Coming. We have our full committee here and online. And this is the defense of Sparse Elguri. He is my first PhD student and the first PhD student to defend by 2 weeks.
Yeah.
And he came to me all of 5 years ago to my office looking to be a PhD student, and just for whatever reason I said yes. And now here he is, 5 years later. So how this will work is Sparse will give his defense presentation, which will be about 40 minutes or so, hopefully. And then we will have some time for open questions from everyone in the audience here. And then I believe there's some time for questions from just the committee. Is that right, Olga? Mm-hmm. Yes, just questions from the committee. And then Sparse will leave, and then we will discuss, and then he will come back, and we will render a decision. So, with that, all to you, Sparse.
Hello everyone, good afternoon. Again, I am Kishan Sukrit, and today I am presenting my dissertation titled Transfer Learning of Guided Waves for Damage Visualization, Localization, and Detection. So the underlying principle to locate and detect sources in many fields start by removing prior information. So that prior information is called baseline information. Right? So one second. So that is very common in fields such as underwater acoustics, where researchers are interested to find underwater mammals, live or dead, or other warheads inside underwater oceans. And also in seismology, where we want to find the seismic sources and other fault lines. And same thing with semiconductor manufacturing, where the defects are found by comparing it with a pristine wafer and seeing where exactly the defects are in different other wafers. So also in structural health monitoring, which we are interested to locate and detect damages in different structures. And structural health monitoring in general is monitoring these structures to ensure its safety, and continuous monitoring for these structures to ensure its safety. And it is very useful in structures like pipelines, where even a small leak could be very huge losses, could bear huge losses. And in aeroplanes, and no same person wants to travel in planes with defects in it. And in railways, windmills, buildings, bridges, manufacturing equipment, engines, generators, and these are all the potential uses for structural health monitoring, and which we want to ensure the safe working of. And so basically, how do we obtain data from these structures? So one such method is using ultrasonic guided waves. So these guided waves propagate through the structure, and the structure itself guides these waves. That's why guided waves. And in thin plates, these are called plate waves or lamb waves. And we use this because they are extremely powerful too, because they propagate very far in structure, and also they're very easy to implement. And another extremely important reason is that they are sensitive to damage. So once we record at the receiver and we record the measurement, there would be the signatures of damage present in the receiver. So hence that is important. And also they are very complex to deal with as well, because of their multimodal nature. That means there are multiple modes that are propagating inside these waves, and also the medium itself is dispersive. That means every wave with our frequency is traveling at different speeds. And also there is multipath interference. That means the boundaries cause a lot of interference. There are mode changes, there are inversion, there is scattering, and a lot more happen when the waves interact with the boundaries. And also they are very overly sensitive to environmental changes, to operating conditions, to humidity, to pressure, to temperature, to a lot more other stuff. So how do we detect damages on these complex structures? Let us look at how these waves propagate in a small 10 by 10 aluminum plate, which is 1.6 mm thick. And what we do is there is a piezoelectric actuator which is stuck onto it, and that is excited at some frequency. And a laser Doppler vibrometer is used to record measurements at every point on the structure. And over a wave field, as an image, this is how the waves look like. and within 30 microseconds, you see the waves interact with the boundaries. And a couple more microseconds, you see it is very complex. Look at it as well. So if you want, that is the exact plate which we used, but the thinner version of it. But yeah, that's a small 10 mm plate which we use for our one of our experiments. And so how do we detect defects and damages on these small structures or these complex structures? So first is we measure a baseline when we are sure that there is no damage to it. And this is how our general guided wave will look like. And you measure at a distance of r or any receiver. And then what we do is we measure the current measurements. We assume that there is a damage. If there is a damage, you get a reflection from the damage as well. You get a direct path and then the reflection path. And what we do is we subtract ideal case. We can subtract both of them, and we can see a clear damage baseline subtracted signal, which we call a damage signal. And then we can use other processes to locate, to detect other stuff. So what I wanted to tell out of this slide is, if we have a good accurate baseline, we can solve many applications in structural health monitoring, like locating damages, detecting damages, characterizing these damages and stuff like that. So what is the issue? There are two main issues with the baselines. One is, as I told you, these guided waves are very sensitive to changes in environment. So these guided waves are uncertain. And at the same time, the baselines are also unavailable sometimes. You don't always have a pre-recorded baseline with you. So baselines are unavailable. So how do we solve these two problems? Before that, let's just look at how the uncertainty is with these waves. So we have three wave field images here. The ideal case, this is a wave traveling with some velocity v. And this is another structure with the velocity traveling with the velocity v. And then there is a damage here at the center, a point scatter. And ideal case, you find the difference of those two wave fields, and you can clearly isolate damage anytime now. Yeah, you can clearly isolate that damage. But however, if I just change the velocity with 1% change in with 1%, you can see the difference is not great. You can still see the incident waves in the difference. And this 1% velocity change can happen so typical, like even some degree change in temperature would cause this velocity changes. And some changes in operating conditions or sensor couplings, you see different amplitude and phases of these waves. And then the baseline subtraction doesn't work. There is nothing that you will get out of the baseline subtraction. And then unavailability. So let's say we can, one way to solve this is I'm taking any other pristine structure. So say I have aluminum one plate with a mass on it, as you can see, that a small mass attached to it. And this is how the wave look like. Anytime you will find the interaction with the damage. And then you have a surrogate structure, another structure with the similar boundary conditions, but with a different material, and we assume that there is, we are sure that there is no damage on it. So can we use any other surrogate structure to do the baseline subtraction? Also, no. You can still see the baseline subtraction is bad. So we have to deal with unavailability as well. So there are three ways to deal with this. One is the ideal way, where we can have a model which is assumed to be very accurate, and then you can use that model itself as a baseline. And which is an ideal case, which is not usually how we can go about it, because it is not always possible to have an accurate model. And then we have a data, we compare both of them, you get a baseline signal. Once we get a baseline signal, you can do the detection, localization, and isolation, whatever, and other applications of structural monitoring. The other method is using an analytical model and tuning that model using machine learning approaches, optimization, parameter estimation, by fitting that data, analytical model to the data to get a baseline. Once we get a baseline, we compare the data to do the fusion. The final way is using transfer learning, where we can I learn the model itself from another data where we know that there is no damages in it. And once we have the data, we can use other optimization techniques to tune this model to get your baseline. Once we get a baseline, we can do a baseline subtraction to do the detection, localization, and isolation. So to sum up my whole 5 years, this slide is what I've done. That's it. Okay. So in this talk, I'll first talk about an analytical model, which was a prior method to this, and I'll talk it very briefly because that will make you appreciate what I've done in the transfer learning. And next, I'll talk about transfer learning based approach, which is my work. And then I'll show 3 different applications of using how can I use the baseline subtracted signal to solve 3 applications: damage visualization, damage localization, and damage detection. And then instead of using a surrogate data from an actual experimental structure, can I decrease my data needs by using any simple numerical simulations, which might not be 100% accurate with the data, but can I still use them to do the transfer learning part? And we do that with 2 different data sets. One is the simple data without any boundary reflections, and assume the plate to be infinite. And then we have a complex geometry data, which is what I proposed in my proposal. That complex data has 8 different holes in it and has different kinds of cuts on that plates. So, and also then I'll talk about conclusions and then future. So again, going back a little step, this was the analytical model where you talked about. We have an analytical model. We tune that model by basically fitting the data to the model. We get a baseline. Once you get a baseline, you can do the detection. So how does prior work do that? Sparse wave number analysis. This is the model-based baseline subtraction. So what the prior work has done is they represented a measured signal as a linear system of equations. So they represented the initial measured signal as a linear combination of dictionary columns, dictionary atoms, and a coefficient matrix V. But what the theory says is the wave number function in these waves is sparse. So as you can look at this is the wave number function, the dispersion curves. If you think of it as an image, all you can see is some random lines on it, and that's about it. So the values are only very sparse on it. So assuming the sparsity condition with a known dictionary from this plane wave approximation, how do the sparse wave number analysis work using that? So first, we collect the test data, and then we build the theoretical dictionary using a plane wave approximation. And then we do a sparse coding to solve for V, which is a dispersion curves. And usually it is done with basis pursuit or orthogonal matching pursuit or other 3D methods. There you can easily get your sparse coefficient matrix, Vy. And once we have the Vy, we know the dictionary, we can do the forward problem to get your baseline Y hat. And so that Y hat basically would not have any damage in it because the dictionary doesn't have a damage. And also, you can do the baseline subtraction once the baseline, but also the dictionary also cannot represent a real world structure because it assumes the plate to be an infinite boundary. And also if a structure has any structural features in it, like bolts, rivets, and these kind of stuff, which are inherent part of a structure, this dictionary cannot represent that. So that is the main problem with this particular prior method. So how do we solve this with transfer learning based method? So again, I'll briefly define how I do this. So we collect both the surrogate data and the actual test data. The surrogate data, as I told you, has a very similar boundary conditions as the test data, but without any damage in it. So once I have the surrogate data, I solve for the D and V using dictionary learning, where I assume both D and V are unknown. So one method to solve that is you basically initialize your dictionary with a random matrix, and then you solve for Vx using a sparse coding techniques like orthogonal matching pursuit or basis pursuit. And once you get V, you update your dictionary atoms with rank 1 approximation, and you do that as a dual optimization problem. And hopefully it will converge and you get a D and a V after the dictionary learning part. So once I have the dictionary, I transfer it to solve a task on a different structure. So now we have a known D, which is coming from the structure which we learned here. And then we have our test data. Using the test data and the known dictionary, you can again do the sparse coding to find the dispersion curves or a sparse coefficients called Vy. And again, once we have that, we can do the forward problem to get the baseline. So it's very similar. If you think about it, instead of taking an off-the-shelf dictionary, we are learning the dictionary from another pristine structure. So let's look at an example problem, a toy problem, to see how this framework works. Okay, so I have a surrogate data. This is a small numerical simulation of plane waves that are moving at some frequency, at some velocity. Then I have a test data. This, as you can see, two things here. The data is different, dissimilar, and you also have a damage here, a small point scatterer that gets reflected once the wave interacts. Can you all see that? Cool. Okay. So once I have that, I use my surrogate data to learn my dictionary. So as you can see, this is what you get after you learn your dictionary. It's nothing but different atoms is what are represented here. To make a simple analogy, it is if you want to approximate any shape of a string, you can decompose that string into a principal harmonic modes, and then sparse linear combination of principal harmonic modes would lead back to any shape of the string. And this is very similar, but in a 2D, in a spatial 2D, where you can get modes of different wave numbers is what is represented in your dictionary. So using that dictionary and the data, you do your sparse regression techniques, and you get a baseline. So now, if you look at the baseline, it doesn't have any damage in it. So basically, since your dictionary doesn't have any damage, your reconstruction will also not have a damage. So then I can do a small baseline subtraction, a simple baseline subtraction to isolate the point scatter. You can clearly see it is the point scatter is clearly isolated. So we actually went ahead and did some experiments to test my framework. We have three different structures here, same structures which you see there. One is aluminum 1, where you take two different data sets with the damage, without the damage, using a laser Doppler vibrometer. And what you do is you first excite the sensor and then record the measurement, and using a stepper motors, you move the plate so that you can record the measurements at every location on the plate. And you have another structure, aluminum 2. Again, same thing, with and without damage. But the thing about aluminum 2 is on the other side, there is a lot of rust on it. So we thought it's a different structure, so we took it. And then the steel structure, which we assumed to be surrogate structure. So we have aluminum 1 with and without damage, aluminum 2 with and without damage, and a steel structure without any damage in it. So now how do we do the isolation on these actual real world data? Very small plates. And also another thing, we chose very small plates because that is how complex it gets with very small time. In very small amount of time, the waves get really complex. So that's the one reason which we chose the small plates. Another reason was the stepper motor can't move too much. So that was another reason why we chose small plates. So damage isolation. Again, same thing. We have a steel structure as a surrogate data. We have an aluminum structure with a small mass attached to it, which is a 4 mm in diameter. So that mass actually will change the thickness of the plate at that particular point, at that particular space, and then you get reflections from it. In time now, you can see the wave interacts with these damages, and you can barely see a small reflection that is coming out of this particular area. I don't even think you can see that, but yeah. So that's a good thing, because then we can learn from the steel structure. We get our dictionary, and this dictionary is also similar to the modes at different wave numbers. But to give an analogy again, it is similar when you have a drum, you impact the drum with your stick. These are different modes of vibrations that you get in the drum. So that is what is learning from this structure. And then you construct your baseline And the difference, I can clearly see a damage reflection from the difference using this method. If you want, there you go. I can clearly isolate the damage reflection, visualize the damage reflection from the difference. So here, in this slide, what I do is I take the test structure, I directly take the surrogate structure, which is a steel structure, I do the baseline subtraction and show that this is bad. And using synthetic baseline created from the dictionary learning, I show that this is a very nice visualization of the damage reflections.
Can I ask
Yeah.
a clarification question? I didn't quite understand the difference between these two rows here.
Okay, sorry. So the synthetic baseline is what you get after doing the dictionary learning. And this surrogate structure is the direct structure, the steel structure itself. So this is an aluminium.
Subtracting it, right?
Yeah. So this is a synthetic baseline which you get out of the dictionary learning. Now, again, we have, as I told you, two different plates. We use the same dictionary learned from steel structure to isolate damages from two different aluminum plates. As you can see, I can clearly see the isolated damage signal, visualize the damage signal from both plates. And so these are the dictionary comparisons of what would happen if I would have used an analytical model using a prior method. As you can see, these are the modes which you have seen before. Those are simple modes, but to represent the data this complex, you cannot represent the data with these simple modes. That's where we go to transfer learning model. And when I talk about the analogy with simple strings, these are the harmonics that I talk about, principal harmonic modes that I talk about. So what else can I do? We can also do damage detection. So instead of measuring every point on the structure, now I only take 5 to 30 or 50 different measurements. And what I do is I compare it with the steel structure. Now I have a aluminum plate with no mass in it and a steel structure. As you can see, the correlation is very bad. All I wanted to say in that is I am using a very dissimilar data to do the transfer learning. The correlation is bad. Now, if I use my synthetic baseline generated from dictionary learning, you can see the correlation increases to 0.9, 0.5, very high, 95%, when there is no mass on the aluminum plate. When there is a mass, the correlation drops from 95, high 95s, to low 80s and 70s. So, can I use the difference of these correlation coefficients as a metric to classify a structure with or without damage, or to detect the presence of a damage on the structure? So what I do is I take about from 5 to 250 different number of measurements, and here I represent the average separation on my y-axis. So the average separation is again the difference in the correlations of the average difference of the correlation from number of measurements I take, from comparing with aluminum plate without any mass in it and comparing with aluminum plate with mass in it. So anything above 0, those are two different clusters where you can easily separate. And as you can see, I can clearly separate out both the plates, aluminum 1 and aluminum 2, with and without damage. Another thing that can be seen in this is as you increase the number of measurements, your average separation increases, so that means you're more sure about the data that you're dealing with. And again, as we use more data, we have greater certainty of what we are dealing with. What else can we do here? Hi, John. Damage localization as well. So how can I even locate the location of the damage? So what I assume is, so only a strip of the plate is accessible to measurements, and the rest of the plate is not accessible to measurements. So that is very common in when you want to detect defects in pipelines, where you can only open a strip of a plate, and the rest of the pipe is hidden inside the underground. So another reason is, if I have the isolation result, I can directly use an energy comparison with every point. So this makes sense by taking only a patch of measurements which are accessible. And this is again inaccessible for measurements. So how do we do the location estimation? The first step of location estimation is damage isolation, which we can do it with our dictionary learning approach, where I can isolate the damage signal. And once I do that, what I do is I generate a model, a plane wave approximation model for every pixel given each sensor location. Yeah, so once I get the model generation yp, which is for every pixel p, and damage signal, I do match field processing. Basically, it's an inner product between the model and the damage actual experimental data. So I'll show you briefly how that works. So assume we have, say, 9 sensors here. After using our dictionary learning approach, all you get is a signal from the damage. And then the next step is using the model. You assume that the waves are propagating in some simple model, plane wave model. And you say, how is my model looking like if my damage is here? How does the model look like at all these locations? And you do that for every location on the plate. And after a while, you finish that, and the inner product between the model and the damage isolated data, the highest inner product would give you the most closest location of the damage. And so the BP is the ambiguity surface, which we call for every pixel P. And what we assume is the damage location to be the most highest valued inner product. Let's see that again with those small plates. I have about 100 sensors here, 100 different locations, random sample locations. And this is the damage which I want to locate. And you can see the yellow thing corresponds to a higher inner product values. And the red and white dotted circle indicates where the damage or the mass is. And you can see how close that is with our dictionary learning framework. And magnifying it, you can see the closeness of the damage with the actual higher inner product surface with the magnified image. What I did next is I compared my results with the prior method of sparse wave number analysis. The only difference with the prior method is how they do the damage isolation. As we have discussed, they use an analytical model to do the damage isolation. So I compare that with the same approach, except that I take the damage isolation from the prior method. So as you can see, these are the highest inner product values are very far from the actual damage. And I do that again with aluminum 2 plate with using dictionary learning framework and still say that it is close. And the other reason I want to mention in these slides is that this is the most average plot that I get out of 1,000 Monte Carlo iterations of assuming that the randomness in the spatial sensors that I take. There are much better images, but I thought this is a good representation of what's happening. And again, this is using sparse wave number analysis. So what did we do next is we varied the number of test measurements, and then we calculated the average distance from the damage. So what is an average distance from the damage is the highest pixel value to the center of the mass is what we call the average distance of damage. We do that with prior method and our method. And there are some interesting things here that happen. One is with the aluminum plate 1, you can see that the average separation, average distance from the damage converges with a very small value. So that goes until 0.1, 0.01 centimeter, which is 0.1 mm, I think. I don't know. Yeah, something like that. And then when you compare the prior method, it converges to a different value, which is about 3.1 centimeter from the damage. So we spent some time on why this is happening before looking at the actual images. We just got this graph and we were like, why did this happen? And once we looked at the images, that's when we got to the point where what SWA is doing, the prior method is doing is, it is locating the actual source instead of the damage. So if your baseline subtraction is bad, you will still have the incident waves coming from the source itself. So your primary source is still the actuator, not the damage. So that is why the sparse wave number analysis method is converging to a 3.1 centimeter from the damage. Similarly, the aluminum plate 2, the sensor is at 4.8 centimeter from the damage. So hence the convergence of prior method to 4.8. And I think the variance here is bigger because, as I told you, the aluminum plate has lots of rust on the other side. So I think that is a small guess which we can make. Because of that, our variance is very high for the other plate. So how can I then use simple numerical simulations instead of actual data to the transfer learning? Basically, because why I'm doing this is because it took us about 6 to 8 hours to get the data from one structure. That structure has 10,000 measurements by dividing into 100 by 100 grid. And the other reason is those simulations are fast to compute. Simple simulations are fast. And so we use a far field plane wave approximation as our simulation, numerical simulation. So here again, I deal with two different data sets. One is a simple data set, which is a huge plate of 1 meter by 1 meter, but the scanning region is just 10 centimeter per 10 centimeter. It is about the center of the plate. And then the transmitter is located outside the region of interest. So all you can see is waves coming from the transmitter into the region of interest. And that plate, I get data from plate with a 2 mm half thickness hole. By half thickness hole, what I mean is it is drilled only half to half thickness on the other side of the plate, where I don't, which is not seen to us. So yeah, let's look at how the data looks like. So I have simulation data, which I don't even think it is visible properly, but the thing which I want to get through this slide is this is very different to the actual plane wave, actual data. I think now a small wave is coming in the simulation. So that has different frequencies, different velocities, different amplitudes, different phases, and everything different. So, and as you can see, a small reflection that is coming from a 2 mm half thickness hole. I do my dictionary learning approach, and I have my test data. I get my synthetic baseline using the dictionary learning approach. So let's look at one image after other. So since this is the test data, we have a first mode that is propagating, and this is a second mode where it comes, and this is where actual damage is. The wave interacts with the damage, and first you can't see any reflections because the wave is still there, and then finally you see some reflections from the damage. And the synthetic baseline, you don't see anything like that because, again, using my dictionary learning, my dictionary doesn't have any damages in it. Once I do the baseline subtraction, let's appreciate this a little bit because I want to wait for a while to see the actual reflections. Well, it starts. Yeah, it starts again. As you can see, you don't see any incident waves yet. These are all subtracted. The incident waves are all subtracted. It's a nice difference. And anytime now, the first wave as well creates a small reflections, first mode as well, which is not seen in the real world data as well at all. And the second asymmetric mode comes here and hits the damage, and you can see a clear reflections of the data, of the damage. Here, this is a time plot, random locations, basically saying that how close my test data is with a synthetic baseline. Okay, now moving to a different plate. This is a bit more complex because two things. One is it has two clamps. The plate is cut into different angles and the corners, so that creates more reflections and making the data more complex. And we have a scan region, and that scan region has 8 different holes on it, varying from 1 mm in diameter to 40 mm in diameter. And this is the region of the scan region, and you can see that the plate is cut at 50-degree angle here and a 60-degree angle here, basically making it more complex from the edges so that we get more reflections. Yeah. So let's look at scan region 5, where 5 is here, which is 10 mm in diameter. The hole size is 10 mm in diameter. Again, those are all half thickness holes. This is the experiment where the data is coming and it hits the damage. You can see small reflections from it. This is a simulation of plane wave. So the simulation now contains reflections as well. Because we used method of mirrors where we assume that the sensors are virtual at different locations. When you mirror the plate, you can get virtual sensors and you excite all those sensors at one time, and all you observe is the reflections coming from them as well. I'll explain in detail if there are more questions on it, but you get the simulation with reflections, which is not at all close to the experiment. And you get your reconstruction, which does not have any damage reflections. And you see the difference where you can clearly isolate damage. And there are other reflections as well that you can see that are coming from different damages, from nearby damages, from 7 and 8 and stuff like that. So you can clearly see a nice damage reflection. Same thing with different region, with different sizes of hole. You can again clearly isolate the difference. And here, what I want to show from this slide is, this is the incident wave, and this is the reflection, reflection from the boundary. So all I want to say that is you are even reconstructing the reflection, which was not possible in the prior method. Another different region with different sizes of hole, and this is a bigger hole. You can see the speed of the asymmetric mode decreases as it enters that hole, because the different thicknesses travel at different speeds. So when there is a smaller thickness, the speed decreases of the wave, and you can clearly see that happening in the subtraction. So that's almost the end of my thesis. What I've done until now is I talked about a transfer learning framework, and then what I did with the transfer learning framework is I did a damage isolation, or called visualization, by visualizing how the damages look like without having any incident waves. And then did the location estimation. I decreased the error from 4.8 centimeter on a 10 by 10 plate to 0.1 centimeter. And then did a damage detection as well on these plates. And then I, instead of assuming data from surrogate structure, experimental data from surrogate structure, I used simple numerical simulations to do the subtraction, to learn from it. And then what I plan to do with this work in future is introduce more physics-based constraints on the dictionary to decrease the search space even lesser, and more deep learning-based frameworks, because that's where the more research is happening now, where more deep learning-based frameworks could also, you can go with much complex structures with that. And also learn a little bit more about the transferability conditions on where can I transfer, when can I transfer, what all the structures can I transfer it to a different structure. And then I plan to investigate more on materials that do not have theoretical studies, where I think that is the future of this work. When there are new materials coming up every day, which doesn't have any theoretical studies, which requires theoretical studies, but right now they don't. So that's where the transfer learning, data-driven approaches would be very useful. And I also plan to do more experiments to get more understanding of what is happening around. And to thank, I first thank my advisor, Dr. Joel B. Harley, and my committee, Dr. Dan Adams, Dr. Tolbert Hastian, and Dr. Vivek Srikumar and Neil Patwari. And I would also thank my collaborators, mentors, and peers. My collaborators are Dr. Shia, Jennifer Michaels, and Jennifer Nichols. And Chris Dimas doesn't have a photo at all online. And these two are the mentors from my Mitsubishi Research Lab. And those three are mentors from Los Alamos National Laboratory, where I was an intern there. And my peers from University of Utah and University of Florida. These are all the publications that went into my thesis. So, thank you. If you have more time, I have more slides, but I think that
That sounds like a good idea.